Okay, now we are recording. So today we are adding, as we said, just some summary for Designing for the Climate from a book which is interesting and you can use as a reference. And then the building efficiency is what we commented on the importance of the life cycle analysis regarding energy. So before that, remember we have a volunteer activity based on the, so regarding that kind of economic analysis of the solar panels. But I think before that, we should comment a little bit on the assignments. So for final, it is already announced. So you have in the lectures. So I think all the explanations are there and you have the samples also. Right. And most of the class has all the, or have all the assignments reviewed. I'm only late with those who submitted late 6 and 7. So for remaining 6 and 7, I will do as fast as I can, but I cannot do before Saturday night. From today until Saturday evening, I'm taking with critics and classes and lessons and so on. So on the weekend, probably they will have a grading, but no feedback, okay? Or not detailed feedback, maybe some basics, because there is no time for more. And I think you need to have this back before to know how you are doing. For feedback for 6 and 7, actually MEP is something we have to do because you may have realized the position of the shafts and the ducts, especially on the ceiling, changes a lot and makes a lot of conditions on the space design. But MEP is just for you to be aware, it's just diagramming. It's important you're aware about it. But 7 is mostly the integration section. It's mostly a section. You can go to perspectives as econometrics, but it's in the section with all where you show your understanding or your designer's ability. So this final section, I think, is the most important part. And most of the comments I did to previous assignments are those. In the checklists in Blackboard, I updated a bit for MEP, but I did a lot of, well, quite a few new comments for integration and green. So green is important, of course, and you have to do as best as you can, but the integration is like the core of the course, like the conclusion of everything you do. And this is one of the comments I do in the Blackboard. But if you don't have feedback, just go to the checklists and you will be able to see what you are missing. But the most important point to all the comments is this. For MEP, how that system affects the design in general, the space organization, and the integration sections, how all those systems work together. So make the section where you have the windows, the openings, where you have the air conditioning or the radiant floor, the lights, all those things, those columns, beams, how those elements relate together to create the space. Okay, so that's the comment. Tomorrow, maybe we will insist more on that, the assignments, and with more samples and more comments on specific things. Today, we will continue with this kind of volunteer activity. So you remember that, well, by the way, one student worked on it. So thank you so much for doing it. It was interesting. And actually that student found a new model of LG panels, which curiously were a bit more expensive than the old ones. We thought not much more expensive, but were a bit more, but were more expensive, whatever. But I didn't have time to update everything. So I will go with the old 2010 calculation. it would be interesting that somebody calculates with 2020, and I will update this someday. At least thank you so much, Hansul, for updating the panel data, and your study was well done. And Min Jong is coming in. So remember, we have a small house in Seoul, all electricity, and we knew this is the tariff for electricity. And importantly here is that depending on your consumption, the price goes up very much. Right. So in this case, even for a 100 square meters, which is not a big house, if you are 100% electric, you are going to the top of the electricity tariff, the 526, which is really expensive. And this is why this guy was spending 6.5 million on electricity every year. It's a lot of money for that small house. So in this case, the idea was, again, try just 50%. This could be a saving, right? And here, we wanted to make sure we would have benefits or we would pay back in 10 years for whatever reason. So here we gave the tariff source for 2010. And this is the calculation of the installation, right? So the total cost of the installation, the area needed. In the calculation, it was 40 square meters, which is about 40% of the area of the building. With the new panels and the efficiency we have, new calculations, it was like 30 square meters, more or less. But you see here a pattern to cover for half the electricity of a normal building. You need about 30% of that building area in panels. So if you're going to have the 100%, you may need like 60% of the area of that building in solar panels. And it's very hard to find so much area to produce that energy. So that may give you an idea on how much you may need. And when you see a real building, you can have an idea on how much electricity they are saving. Maybe it's not even 1% in most cases. So the detailed calculation is there, and I should stop the numbers there. So when you make the net present value for the 10 years, just in the first year already we have a benefit, which is amazing. Well, the second year actually, right? So the first year is paying back. The second year, you have some benefit already. And in 10 years, you already save 26 million, which is a lot of money. And this is telling you that there are cases in which making those installations make a lot of sense. If electricity is as expensive as it is in Korea for households, it makes a lot of sense. And you see, when you reduce the consumption by half, the basic tariff also gets down. So you don't pay the 500 won, you pay probably 300 or 200, whatever. So that's annotated here, right? So we reduce the consumption, and then that's the next step of energy. And then you save a fixed tariff of 1 million per year only for using less energy. So you save twice in houses. If you have to use clean energy in house in Korea with this kind of tariff, I think it makes sense always, provided you have the space and the sunshine to have those panels, which not always happens. With the public buildings, with companies, with the offices, it is not so clear. It is, as we saw, it is in between space, right? And in this case, of course, you sign and you go for it because you save money instantly. And remember, we have a question which nobody replied, and it's okay. In that cost benefits calculation of electricity we just did today and we did last week, you know, the governments give you help, subventions, subsidies to reduce that cost, that problem. And the question was, should we consider those savings in the calculation so our benefit is larger, or we should not? And that was a question which is not true or false, it's about opinion. And I couldn't find every year, but I found a survey of the first building system scores. And actually, half the class telling, yes, we should include that help in the calculations. And some people said, no, this is a benefit, so we don't spend that money. So that's not in the costs, right? So it's like really 50-50. And some years, some opinion is higher, some opinions is less, but it's interesting that there's not a clear idea. So it's okay, you may have your opinion. I will tell you my opinion, my personal opinion, is that we have to include the total cost. Because we're speaking of the real cost benefit of the system, right? And the government money is personal saving, but still is money, right? Which comes from somewhere. It's money from the system. So we are thinking on sustainability, not in terms of personal economy, of personal business, which we do, of course, but as persons which are concerned with the real improvement of the environment, we have to see the real cost of the system, right? So some money is put by us, some money comes from the taxes or from the government, but it is all cost. And then we have to know how much we are spending against the benefit, because our personal benefit is just our individual business, but it's not really helping us to understand how the system is balanced. But again, that's an opinion. And some student put a question. This is the handwritten of the student and mine, which I think mine is worse. But again, how you decide regarding those systems depends very much on your own vision, your own possibilities, right? And whatever. So everybody wants to have things better, but the moment you have to use your own money, you're less idealistic. And you expect somebody else to help with that. That means we're not so idealistic sometimes. But well, I have the text there, the whole discussion, and I already told my opinion, so let's continue with the class. So the first part of today's short and light lecture is just collecting a set of diagrams from this book. This is one of the many books you have for helping you practically with sustainability. And I think this is a very good one. It's not very theoretical, it's not very detailed, but it gives you the solutions in context with the general climates of the world. It's kind of a very practical, very contained handbook. It is used by a lot of people, and it's basic reference even in schools. And well, I brought here just a few images as summarizing it. It's not, what I put here is not instead of the book, but still is a nice summary of strategy we may use. First thing, I think, I'm not sure if you are familiar with the psychometric chart. That's a very complex chart and very well thought, actually. So it has like many dimensions. One is the degree of humidity. So from saturation to dry to very dry, totally dry. So 10% is almost the desert's air. Madrid, my hometown in summer is about 15%. So it's like desertic climate. So with those parameters, so you know our perception of comfort in terms of temperature and the environment is a combination of air movement. So you have also wind speed in this chart. You have humidity, temperature, air movement. You have a total enthalpy of the system, is the energy embodied there. I'm not sure in this chart where are they. So the lower part is the temperature. So basic parameters we use is temperature and humidity, relative humidity, which goes that way. And somewhere is the wind speed, which makes for the air, which is in meters by second. So, of course, the comfort is subjective, this kind of area. And we think most people statistically is comfortable in a range of temperatures. So in very dry environments, you can go to quite high temperature. And then as you increase the wind, so as you increase the humidity, you tend to feel cooler, so you are less comfortable, right? And so happens with the wind. So there's an area on the combination of those 4 or 5 parameters in which people feel okay. And with colors, you have like a kind of involvement of the world 6 climate areas. What is a 6 simplification? So if you think, for example, of Korea, Korea is not at all homogeneous, all the same climates. And if you forget Jeju, even there you have like different areas which are not exactly the same in terms of climate. But to compare solutions along the world, I think this division is quite interesting. So probably most of Korea is in the blue, temperate climate. But some students, so we have somebody from Dubai, so you have the desert, coastal climate. But Madrid is something in between desert, continental, and temperate climate. Because the plains of Spain are at times like a really, really desertic in a sense. So, and then you see how that combination of parameters changes, for example, in the very, very dry desert, how cold they are in the poles, for example, and so on. And you see that when the environment goes out of this zone area, we have to change other parameters. And sometimes just increasing wind speed or shade or humidity or drying air is enough to bring that comfort back. But sometimes we need, when you're in very extreme areas, you will need those active systems. So important, this chart. This is a sampling of cities, right, with those kind of climate areas. And usually, I don't know why in Korea they put Pyongyang, not Seoul, but whatever, I think this included as a temperate climate, as most parts of Europe and so on. And Madrid is also considered as kind of temperate climate. But of course, Madrid is not the same as Paris at all, or München. And this is in general, right? So you have this kind of comfort area. So if you go very much humid, you just can dry the air. Or you can just, when you're very dry, you can humidify, and that humidity will bring back comfort. The evaporation, we commented when we saw Alhambra and this kind of very thin water films that many Arabic cultures use. So that evaporation absorbs a lot of energy and cools a lot. And sometimes you have to go to the active systems, right? Like cooling and humidifying. This is the Korean summer, right? Only dehumidifying, as we said, and this is again active, right? So we have to sometimes heat and humidify in very, very dry areas. This is also Korean, actually, this is Spanish, Korean winter, right? So we need heat and humidity. And this is Korean summer. We need to cool and humidify. So sometimes you see proposals for Korea imitating or trying to import some kind of Arabic wisdom into Korea. And the evaporative cooling is one of the proposals. And it would not be very wise because in Korea, in summer, the humidity is almost saturated. So that evaporation will not work, will not make things better. This is why we need just to take humidity out. Whereas in very dry climates, that works very well. And that is why that system was very successful in Spain, because as we said, in Spain, we have in areas like a very much, at least temporarily, that kind of desert climate. Okay, so psychometric chart is really basic whenever you deal with the temperature and comfort. And especially for cooling, because heating is very easy. But cooling and humidifying is really, really hard. And that changes a lot the whole feeling of the environment. As an experiment, if you go to the Seoul Energy Dream Center, if you go in summer, so we did a visit a few years ago with building systems. It was June. It was really hot. They have this kind of a experiment. So in the first floor, they have a floor cooling plus dehumidifying. Otherwise, the floor cool with condensate water and there will be a splashing of water. So they did both things. And the second floor is like a high quality air conditioned. The air conditioned just humidifies by itself. And you can see the difference in feeling in both areas. And they are both top class systems, really well calibrated. If you're lucky with the person in charge on that day, you remember those buildings are not easy to manage. But if you go to the first floor with that cool floor and this dehumidifying, it feels like perfect. You go to the second floor, I can feel this kind of air-conditioned dryness and this kind of unnatural and more unpleasant feeling. So it's really nice to experiment all those changes in the same building. And this is why I think in Korea, if you can solve the humidifying, since you already have a ondol for heating, using ondol for cooling is best solution. I installed it in a few places in Spain. Luckily in Spain, it's in Dubai, summer is very dry, so we don't have that run of condensing unless you go really, really cold. But you don't need to cool up to the dew point. Okay, so interesting comment. So I just collected the image with the summaries because it is very well expressed. So as usual, we start from the section of the building. And you have the clean systems like a photovoltaic system for electricity, solar cooling, solar thermal system in which you just heat directly the water to have heat. Some protection for windows and thermal protection, which means like additional insulation, right? And then this is the kind of environment you're looking for in terms of the lights. And you remember we're already familiar, 300 to 500 lux is like a working light. For ambience, you can go a bit less if you want. The temperature, range, humidity, and so on. So with this target, this is the kind of passive and clean strategy you can apply. And you have the choices. And here they tell you cities or climates where they make sense or where they might be used with some limitations. So the ones later are less effective, but still can be used. And then of course the window variation and not ventilation. You know, if you open the windows at night, especially in summer here in Korea, for example, at night it is still cool. You can refresh the building. Imagine all the university buildings opening automatically the windows at night and the whole building cooling. So you come in the morning, the building's already cooled. You don't need to have a shot of strong air conditions every morning, which is a huge expenditure of energy. So this is again, very basic. And soil use is to use like a geothermal in many variations, can be very simple. Most of you want geothermal to very deep wells, and it is the best system. But for more small buildings and more modest budgets, you can just cool the air in the basement, or you can have just the water going just not very deep into the ground. So you can just have some cooling and heating, and still might be effective in some systems, right? Use of groundwater, and we said in Seoul, we keep pumping groundwaters, and that's some water we could use to exchange energy. Okay, and then you have those summaries, those strategies applied to the bits, to the envelope, to the interior. And see, again, we always start from the section. So sections are telling all of the building. And perspective section is also okay. Perspective sections or axonometric sections are very used, but first you solve the section, and second, you visualize the perspective, right? The perspective, the axonometric or the perspective. You have the three-dimensional image, and that helps a lot to explain and to understand the system you are using. In this case, you have like integrated photovoltaic panels in the windows. So you have the double effect use of shading and also collecting energy. They're integrated just in the facade, in which you can have more density of panels. The very basic sun protection. And you know that solar protection works better when you start from the exterior, so the heat doesn't come inside. When the protection is inside, you regulate light, but the heat is already inside. The natural ventilation, it's amazing that still many places are not allowed to open the windows. And you remember we commented in Korea, traditionally you can open the whole room to the exterior, but we keep building those curtain walls with tiny, tiny windows, which are really, really suffocating in summer. So this kind of opening is something which we could consider seriously in the climates, or the automatic aeration, which we see in cooler climates. And again, this could be useful in a Korean winter, in which you still need fresh air, but you cannot have all that heat loss. And finally, some of you mention very often this kind of solar protection glass, in which you have less radiation. But remember that usually less radiation means less light also. So you might be saving in one side, but not in the other. And even just a small radiation filtering may reduce the light you get in by 50% or more. The window I have in my office, Changwik one, is like in between. So it filters a lot of heat, and that's nice. Especially now in summer, I have morning sunshine. But when I open the window half, the light I get in my desk is twice as much as the light I get with the closed window. You can see the difference. And that means using more electricity in general. So very nice collection and very well visualized. And you cannot use all of them, but you can see, well, you have them visualized and see how they apply, and you can just choose them for your project. Then daylight, I will not comment more. This is very nice diagram, but we gave more tools. And actually, if you really want to be serious, you know that you can make simulations very detailed. But okay, like all glass with the resulting light, dark walls actually will reduce a lot of light. That solar filter, you see the difference of the solar filter, in which you get light very, very limited, right? To have some parapet, to have a top and bottom, and to have a smaller window, and so on. So that's kind of the common sense. So usually, remember, as a rule of thumb, we give if this is the height of the window, we consider we have a acceptable light to twice the height. This is why usually we think for the usual 2.5 to 3 meter ceiling, we think rooms of 6 meters depth, 5-6 meters have a nice natural light. They don't need more. You may have experience with the classrooms in which next to the window, you're happy. In the central rows, you're okay. But if you're on the opposite side, you will depend always on the artificial light. To have nice light level. And then finally, the interior environment. Remember that this was one of the lectures which seemed very abstract, because we spoke about light and then sound and acoustics and all those things. Here we have the noise, the air quality, the sound reflection, the sound level, which you know that they go together. So that's the reverberation, which sometimes we want to have it longer, as a kind of concert hall, or shorter in a meeting room, or somewhere where you have to speak or have a speech. We saw the combination of air, humidity, and temperature. And you could say like also air speed. if you have air conditioned or you have fans in terms of the cooling or so on. And finally, radiation. And you know, you can radiate heat or also cold with the on-door. So you can use both. And radiation can be on the floor, on the walls, and on the ceiling. So this is exchangeable. Many places have like a hot ceiling and cool floor, and they choose what to use each time. And sometimes you see them also in the walls. It depends on the possibilities of the building. Like airspeed, okay, it was here. So, right. And of course, you have like the solution you have in the air from the ground, from the floor instead of the ceiling. You need to have the return air and so on. So again, this is very nice summary of things you may want to consider to define your interior space. And again, when we studied this in MEP systems, the different solutions you have to address this cooling and heating, right? So I will not elaborate on it, but as a summary of solutions is nice. What I ask you, if you decide some of those are good for you, just please don't copy and paste right away. So better choose and figure how to integrate. That means how to adapt to your project. Okay. And then the green energy. It was in the diagram, but we have from direct fluid heating for hot water, which is very efficient. So efficient that this is mandatory by law in Spain. You need to have all or big percentages of hot water by sunshine because we have so much sunshine there. And all the systems we provide have either shutters or fans because in summer they overheat. So we calculate for winter where we need to heat more the water. But we realized that we have too much sunshine in summer, so we produce much more energy than we need. And this is something which is solved by putting shades or fans, which is a bit crazy. There's not so many ways to reuse that energy, for example, we could use that, but I didn't see commercial systems working on that, for using that additional energy for producing air conditioned. Again, photovoltaics, we know it have in many ways. The problem of photovoltaic is the storage and the demand. This is why when it's possible, you have kind of two-way connection with the grid. So you will absorb energy from the company when you don't produce enough, and you will return energy to the companies when you don't use it so much. So everybody can benefit from it. And the storage, you know that there is a set of batteries for family use. I think Tesla commercialized something. I don't know how it is now in the market, but you have this possibility to, instead of return that energy to the grid, you can store for yourself and you become independent, which is a very interesting possibility. Then you have the heat exchangers. In this case, for the geothermal, and this is the two versions of geothermal, like the very deep, when you go to the layers of the ground, and we have a lot of energy stored, right? And you can send a kind of a cooling or heating fluid with a large or very high specific heat, so you can store a lot of heat, and you can exchange for your system, and you can cool and heat, or you can use the most simple, just cooling the air through the basement and pushing it inside. You can have something in between, so you can have that water fluid going just 1.5 or 2 meters underground, and that will also give you some help. And finally, you have this kind of cooling towers, which are active in reality, but something that I wish you use more is that heat exchanger. Heat exchangers nowadays are very efficient, so they are over 90% of efficiency in the exchange. So especially in ventilation, I don't know obviously, you're all copying diagrams because I see identical diagrams in assignments, which are not exactly the same. Sometimes I see the lecture, sometimes I see others. And many of them have this kind of exhaust air intake going to the cooling or the fan room. And there is a proportion of the exhaust being mixed, right? And there's a percentage of mix of exhaust and fresh air, which is very traditionally done because that saves energy. So you may mix it 20%, 50%, 60%, and that's an air you reuse. You still have fresh air so people can breathe, but the efficiency is small. And you know you are mixing used air with new air. So especially in a time in which we're worried with pandemics, it's not a good idea because you're recycling all those viruses and bacteria through the system, but also because of the smells. So that's not a good idea. Of course, you can use it if it is legal, but you have also the plan of recycling or recirculating pathogens. That means bacteria, virus, and so on, but also smells. If you put the return air to the bathrooms and the kitchens, you can recycle it because then you will smell whatever happens in the kitchen and the bath to the whole building, and that's terrible. And sometimes people make that mistake. Instead of that, you put a heat exchanger for air, which is over 90% efficient. You have all the advantages of recovering that energy, and you have always clean air. Right? So please update your sources or remember this. It's not much to remember, but that's important. Okay, so that's so much for the summary of strategies, which I think is very well done. Again, the book is a whole book, so it's much more detailed, and you may want to use it as a reference, especially if you work in different places. If you are aiming to work only in Korea, that's okay. But if you are curious to see how things change in different climates, that's not the only one, but very basic and very practical book. And I have not any connection with the editorial or the authors. I don't know personally, but I came across to it and I can only recommend it. It's kind of reference. Beyond building efficiency, it is a summary of an article we published a few years ago. I mentioned in class, but I wanted to show you a little bit of insight because it gives you a few hints on many things we ignore in terms of energy efficiency, like in buildings. And this is a case study. So this is done by myself and one colleague in Spain. Actually, he did the hard work. I just checked things and prepared make it scientific for the article. So this is the traditional town in southwest Spain, and you see here you can see a new planning to create a small danchi for individual houses, which due to housing crisis in Spain, it got stopped. So it was an opportunity to see for alternatives in terms of sustainability for that small development. So it's very specific case study for a specific place, which was the climate I said. So winter is kind of continental temperate climate, but in summer it's like a really desert. It's very comparable to Sahara with a bit more water, more agriculture, but very much similar to Sahara. So climate is extreme. It's like 3 hectares, not very big, and it's about for 160, planning was from 160 family row houses. In terms of Korean danchi, this is a really small thing, but for a small town, it's the important proportion. So in that case, it meant a lot of impact. It's small enough to study it in detail. So this is the kind of development. It's not good or bad. So design is bland, but this is kind of housing which was trending in Spain since the 1990s. Individual house with small courtyard or parking and a small garden in the back. So low density and very much individual space to live. And they are all stick together. Right. So this is like the 1990s thing, and still planning has separation for those kind of buildings. And they were popular, but they're extremely inefficient in terms of energy use and also embodied energy, because you need to urbanize a lot. And this is what we studied. So I will not go into much detail. What we did is to study energy and CO2 emissions, which are related but are not the same. Urbanization is all the infrastructure, like creating the streets. What we have in my image on the back, this is pure infrastructure. So there's a lot of energy and CO2 to the atmosphere. Just to make an introduction to the big island heat we are creating in the center of Anamdong, and then the construction itself. I will comment on this later. Then the same, but in 10 years of use of building. And why 10 years? Because after 10 years, people start making renovations and changing things. So we have additional construction and demolition costs in terms of energy and emissions, and so in terms of money. So we thought 10 years is a good period, quite realistic. And if we go to Korea, where the average age of buildings is 18 years, also makes sense. And then we compare both in both sides, and we said the conclusion. So it's very easy, very simple system. The LCA, life cycle analysis, is normalized. So there's the ISO International Standard Organization, has the 14,040 and 14,044. They normalized how life cycle is organized, and it's international. Any country in the world will use the same parameters. And I reproduce here the basics because this information you have now, which in class we said more in concept. Now you have the practical way it is done. So production is fabrication, is A1 to A3. It's not a paper size. It is the like a prime materials, transportation, manufacturing, and so on. Then the building process, which is 2 more steps: transportation and installation and construction. Then the use, and then we have the end of the cycle, the demolition, the construction, and so on, which is also, you see, you have like 4 possibilities. This should sound familiar because we saw in the lecture, and now you may learn, or at least know, that production and construction is A, use is B, and the construction demolition is C, right? And they have numbers depending on that stage. And then you're really an expert. So what we studied is the whole production and building process, and finally the use, maintenance, energy consumption in those first 10 years. We ignore all repair, replacement, rehabilitation, and we also ignored water consumption because we're concentrating on energy and the carbon emissions. This is what we did. So here we are telling the software we use for each part. So for construction, we have urbanization and building. We analyze and we calculated the CO2 emissions and the cost, right, for both the urbanization, the infrastructure, and the building. CO2, energy, and cost. And then for the use, it's a bit more complex, but still you have the MEP and the energy calculation. This is based on the US, so US Energy Department open program I commented in the class. So we calculate the thermal load, and then the energy, the solar, the climate study, and with that we calculate all the installations, and then we make the calculation of the energy consumption and the CO2 emission, and with this we give the energy rating, and this is for the use of the building. Those 10 years, here we say if it's energy A or A plus or B or C or D or whatever. This is what we did. This is very rough. So to do this, we have to make the real design. This is not, do not see this as design, because it's not a real project. But you can see here the row houses and the low density multifamily houses. This is what we call villa. So it's like a house, and this is villa, right, in Korea. This is 4 floors. This is 2 floors, but it's all individual. You can see that instantly you need more streets, right? So it's a big proportion of streets compared to just one street, which will give access to all blocks. And of course, much more open space where you have the blocks for exactly the same area and same program of house. And of course, it is in all cases is 16 or 160. So we compare different typologies for one family house and for multifamily, and we chose the ones which were closer in terms of orientation, sun, north, south, and also in terms of a volume related to surface area and the facade, so they were easier to compare. The most compact block has much better, more compactness. That means you have less area for the same volume, so you have less energy heat, energy losses. But we thought we have to compare solutions as close as possible. Right? So these are the two solutions we compare. This is why. This is the result of the row houses, and this is the result of the blocks, in which we have time to or money to put a swimming pool in the garden. So this is the summary of both the built area, green space. Of course, the multifamily has much more green area, right? Like almost 0.9 of each built square meter, but it's more than 3 times the free space. The total energy used, the CO emissions, and the costs so there, and of course, multifamily rates better in almost everything because it consumes less energy, has less CO2 emissions, and so on. This is just unitary comparison of buildings. So everywhere the multifamily rates much better than the multifamily. That's not surprising. What is interesting to see is the graphs. So we have energy and CO2. In blue is the one family, and in green is the multifamily. So you see everywhere blue is bigger. So one family is less efficient than multifamily, that's obvious. But you see that the infrastructure construction and the building construction compared to 10 years is a lot of energy cost. Actually, infrastructure is very much comparable to the whole of the 10 years of use. But both together are a huge amount of energy and emissions. By the way, in this graph, let's say, okay, let's restart this slide because I think I messed a lot. What you see in the left column is energy, and the red column is CO2. Of course, CO2 tons, well, the units we use, it's not that it's less, we use different units. So we have for the construction period, energy and CO2. And then we have several alternatives for energy use and emissions. And the problem is that the regulations give more value to have less gas emissions, less carbon, than less energy. So you will see that having something as bad as D and C, you have very small energy expenditure, but a lot of carbon emission. If you have B in both cases, we spend more energy. So it's better rating, but you have more energy use, which is crazy, but less emissions. So this is counterintuitive, and this is something you have to be careful because sometimes saving energy is not the same as emitting less or more carbon. And then when that comes, and you know that each step is more expensive, so just by changing the systems, we got B. By making better systems, we get A, which is the best rating. And we have the tiniest carbon emissions, but they are more expensive. We are more ecological, we pollute less, we produce less greenhouse gases, but we spend more energy. So we spend more money in the system, we spend more energy. Who will decide to choose a system? So that's a big problem. Not always they go together. So something which we didn't know, we discovered by doing this. It's not so much published, not much comments about it. So being energy efficient and being low emission is not always the same. And here we calculated in detail, and there's no mistake about it. Of course, it depends on the modeling also. It depends on what the low primes. But you see that going from B to C, the benefit is tiny. The difference is tiny, tiny. It's very small for a lot of cost. Well, that's the comment of this slide. So we had a better rating with less energy efficiency, which is kind of surprising. And you will have a hard time to convince any client or any corporate client with this. And again, those reductions are really, really tiny. So you have to think if really it makes sense to aim for an A rating if you really have not savings, which are important. Remember that during the construction, you produce all that carbon already, and see the savings you're having in between those elements. So the problem is in the construction and in the urbanization, mainly. Even if you multiply this by 10, the difference is tiny. And this is the diagram we saw in class, right? In which we forget about everything, and here we put together energy and emissions. Actually, in terms of percentage, it's not so much difference. Just be aware that it's not the same, but we calculated that urbanization, infrastructure, and construction account for 93% in terms of low efficient construction, and as much as 92% in very efficient construction. So in 10 years, 92%, 93% of the emissions are just already done. And this is what is happening with our DR parking. So all this, we have no building, but all this percentage is there for life. Okay. And this is why that analysis is important. Because see, we keep demolishing and building like crazy. And it doesn't make sense, because those buildings being more efficient means you will still need 40, 50, 60 years to compensate for that huge impact you did during the construction. But apartments are demolished in 30, 40 years, so it doesn't make sense. And you see the construction, it is all, and you can go to the campus and see what they're doing. Old diesel engines, all diesel engines producing black smoke. They are not ecological cars anymore. And this is huge, powerful machines spending, polluting non-stop. If only this was more carefully done, so we have to build at some time. It's not just a problem of building too much, to have cleaner machines, to make sure you demolish only what you need, that you excavate only what you need, right? Think all those mountains, full hills that get demolished all around Korea, not only in Seoul. You go to Yangpyeong, you go to Incheon, you go to Gangneung, and you see full mountains disappearing to have just a flat land to put a building without having to think too much. That's all not only destroying that beautiful Korea you have, or we have, if we consider it's part of the whole world, but also polluting and creating emissions like crazy. So, of all those conclusions, I wanted to insist and repeat and to make you clear that we have to reduce urbanization and building activity. And when we do it, that energy and emission impact is enormous. So we have to address the way we build to reduce that impact, which is 90 or 90% of the whole construction industry impact in the environment. You have here the links, so you can have all the calculations and all the article. It is very boring. It is the hell of a work, but scientific. And we compared with other publications in Europe, in China, There's a lot of research going in China, and the results are very similar. It's not very different. Just for your information. So enough theory for today. Let's go to the construction sites, which are fun. Let's go to the presentations. And I have to look for number 4, which is open. Let's, oh, it opened. That's great. So I collected 2 sites, say the exceptional and the common. Exceptional DDP by Zaha Hadid, and then Centropolis by Posco. It's very short. Actually, they're both short, but I think both interesting. And this is a nice photo. So I visited it last time in 2012, and the exhibition they have is Catastrophe, which is a very nice cover for DDP, which is, again, it's not a bad project, and it may be among the best built works of Zaha Hadid architects. But it has some part of catastrophe in its genetics. Centropolis is like a very much plain building, but it has interesting things we can see. So I visited DTP construction 3 times. One with Granada University, one with Songkyung-Kwan University, and one with Korea University. This was my first teaching semester here at university. And this is the photo of DTP in 2012, already 7.5 years ago. Well, you can see a very nice state of the facade in process. Okay, this is the vision, and that time, much of the activity was done outside. So there's a desperate move of the city of Seoul to have some activity there. And a lot of pamphlets telling about the future, which was nothing what came in them, but let's concentrate on construction and see here how much you needed, like those cranes to work on the roof. It was very hard to work building because people could understand here it's dangerous, and they need a lot of additional machinery to keep it going. So again, this is all polluting diesel, working there for years. So I'm not sure the ecological calculation of this building is accurately done. This is the first area which was open in 2012, I think, or even before 11. And you see just open that concrete did not result very well. And a fortunate thing of this construction is that the concrete industry improved after this building. So there was only one kind of concrete for everything in Korea, as I heard. From here, you can choose different qualities which make a better result for fair face of just exposed concrete. Okay, so they were doing Fashion Week, and we took the hobby of taking photos of the cracks of that concrete just made and how dirty, how ugly it looked. Well, this is a nasty photo. So this is about design. It was supposed to say, it was the planet to be the design mecca by 2015. So I don't know if anybody thinks the design mecca. I'm not sure about the spelling of it. But if you want to be design mecca, you have to design better graphics. If you go back to a lecture about visual communication or the site, right? When we saw the interior, this is the perfect design for people not to be able to read clearly. Same color as the concrete, a glass with shades on the back, blurry always, hard to see. And you see this is from eye level, so it's too high. You have to look up to understand what they're telling. So bad design in the design mecca. A lot of introduction, so they have beautiful models. This is your, actually most people already graduated. I can see their faces. So this is Unsol working in Unsandong. This is Yoongyun working in Changzhou, I think, and so on. And this is the first part. This is familiar photo because we use this to explain the crazy structure at DDP, but it tells you huge concrete core to counterbalance this ugly and the brutal cantilever. There's no high technology here. This is pure mass of steel. And the cooler three-dimensional frame wrapping around this structure, which makes for the shape and holds both the outside and the inside envelope. This is how it looked. This is official photo. The problem with TTP is that for much time they forbid to take photos. They thought the technology was very special and they were very serious about not photographing. So the photos you have from the site are hidden photos, but this is official. You can see here the brutal platform with this. This is almost solid steel. If you are familiar with the cantilever, so this is a nice three-dimensional structure. This is a brutal structure. And you see the size of those cantilevers supporting this huge base with that enormous concrete counterweight. Then the three-dimensional structure wrapping around and already getting the first envelope and finally the final aluminum tile. So this is really nice photo which shows you the whole process of that very difficult construction. These students, and this gives you the scale of this mega truss. So the thickness of this element is almost 1 person size. In steel, that's crazy. And I didn't see the construction, I don't know how it works. And you see how it is painfully anchored to that huge concrete mass. And then a bit more casual structure just to complete this kind of a blobby shape. Again, this is the explanations of the building and the envelope. This is the sample of the three-dimensional structure. This is very similar to the one we saw. It's balls with how many? Like 6 connections, like a cube, which you can rotate and you can put in any combination. So just by adjusting the length of the individual elements, you can make almost any shape. And this is done by order, right? This is the envelope, so double layer of insulation with some rigidity elements for rigidity. So this is oriented strand board, and then some polymer sheet, which is expressed there. I didn't memorize it. And then the finishes for receiving later the aluminum or the interior finish. It's aluminum panels. This is one of the smaller ones, very sophisticated. They say that the cost was between 2,050 to 400 US dollars per unit, which I would question. Maybe it is like that, but it's a really expensive panel. And they are not polished. So they are matte. So they do not reflect the sunshine because that huge aluminum mass would be very disturbing to the neighbors. So that's a very considered thing. It was not the architects, it was the city major who ordered for that. Because I think the initial design was shiny. And the shiny building in Dondemon all around would have been quite difficult to handle. But well, this is all aluminum perforated to have some transparency and to lighten and with the lower, so it is self-rigidized. Quite thick aluminum, very good quality, very expensive. The solar panels, again, we spoke enough, and this is 2010 technology. I don't know how much percentage of energy they use because all the totality of TTP is artificial elite. Is no windows building, which is the other thing I would question. There's a few windows in the central lobby where they have the shopping center, but it's really mostly no windows building, it's total interior. So I don't know how they work in terms of efficiency. This is again official photo from the pamphlets, and this is a very nice view again of the basic steel skeleton. This three-dimensional structure, which is I think it's a beautiful one, it's very well done. This is where the BIM system worked well to design all this. And with a secondary or intermediate structure, and then the typical beams and just like I don't know if this metal prefabricated slab to complete the shape. So this is almost flat, it was very well, but the wobbly area is the one which took a lot of effort, and they have to just assembly one by one. This is already with this layering we saw before, just ready to get that waterproof of that sheet of vinyl and the final cover. And curiously, this was not enough, so they just poured They just over this, they literally poured polyurethane paint to make sure it was totally enclosed. And this is one of the reasons they don't have windows. Putting windows here is a pain. In some areas they have, on the display, they have openings and you can see light again, but this one is so difficult and windows are a complication they didn't want to have. And you have this kind of exception space without, you have the black box. Well, nice and very informative photo. One thing, well, I would go back to one slide. We are almost finished. You see this blue thing here, also in the excavation. If it rains, things get messed up. So when you have some sensitive element like this kind of timber finish and so on, you protect it just in case it gets wet or dirty. Because to apply this vinyl and the paint and the layers, it needs to be clean. You don't need to accumulate a lot of powder. You see also the waterproofing of this big area. This is, I think, if you're a waterproof maker, this is kind of happiness, photo of happiness, like thousands of square meters of. So this is what I said. In the end, there is a final layer of polyurethane. It goes moving in all directions. So I don't know how they did counter the gravity, but in most places you can see even the drops of the polyurethane going down. And then individual supports, very expensive, sophisticated, to get all those individual aluminum panels. So you have this multi-layer envelope with this cover, and then individual elements to fix the aluminum panels which make the facade. And there's like, I remember it's like about 50 centimeters of space in between. And this is ventilated. So water, air, and air comes in. And then it slides and gets back again out. You can see here in process. So when the curvature is very small, the panels are smaller. Some places the panels are almost flat. It's quite okay. You can see here so how the polyurethane is applied. So it's just like a paint pouring down, it's applied, but you can see here the layerings. And over this is this fracture I commented to have those panels fixed. You can see here in between, this is new panels which are protected as they come from the factory. Yeah, they're in process. You can see better here how the individual supports are waiting with this kind of 4 cross system in which you have individual anchoring points. You can see here the section. And this is a hidden photo, this is 2011. They had, this is the guy explaining things. They had to test every panel after fabrication. They have to test them and calibrate, send them back to, so they make the first mock-up panel, they calibrate it, they send back to the factory, they brought it here. This is a mobile platform, so they know the exact shape they need. And the panel went to and forth like 2 times, so they had to test 3 times and they finally applied. This is why I'm not sure about that cost of $300 on average per panel is accurate. Of course, maybe doing it by traditional means would be like 10 times as much, but well, it was not easy thing to do. And this calibration on site was quite impressive. This is the system. So they could change the shape and they will see how the panels resulted. So if the tolerance was not exact, they would order a small correction and they will have the final panel. But it shows very well how the system is working. So I think it's very nice construction section. And here everybody happy for the photo. And then interior is the same. It's a huge metallic structure in which you have the same, but finishing materials are easier to manipulate. Right? So just by cutting and bending timber in this case, remember that you can do this with also gypsum panels. And then using polyurethane just for gluing things together and having some kind of absorption. Remember, this material is a dangerous one. And again, fabrication had problems and there is a lot of research. So there's quite interesting work there. And this is the back. Again, no mystery, just a kind of a steel grid with just bolts and with welding. So this is something you can do on site. And then just adjustment elements to connect. In this case, this is kind of gypsum. I don't know if it's gypsum or more sophisticated Korean element. But those shapes are just the same. It's like the typical drywall, but with the sophisticated shapes. Again, they're very difficult to fabricate triple curvature elements working the same way. There's a kind of net to support it, and then how they are installing it. And this is the photos of the interior space. If that photo ever moves, it's a huge structure to collect all those wobbly elements, and this in between is just lost space. If you see the section, this kind of huge cantilever, and the space you use is this tiny thing inside. The rest is just a structure, which also makes one question if this is really intelligent way of using space, because there's nothing grandiose as you would expect from the outside. And when you go look to the top, the inside is a mess. This was an example of a BIM precision, but I see here a lot of human improvisation during the construction. But well, that's not the official thing. More interior, I think they're repeated. Did it go back? Well, it's interesting because the track site construction system is the same as the DDP itself. Okay, and this is one of the smallest groups I had in a construction site. And we're already 2 minutes over the time, so maybe Posco we will see later. Only one thing to comment here, this very common building. Posco was great. They gave us a lot of cookies, which everybody ate instantly. And the Posco people were thinking students at KUA do not have money to eat. So the point is here is the construction of the basement walls. You can see here the drill, the piles, then tied on the top to create this kind of retention wall. And then afterwards you have an additional wall to make the finish over there, right? So that was the moment. And you see here the water coming in. There was a question there. What we do with this water leak? But this is interesting because the water will leak inside. And this is central Seoul, which is not a Gangnam area. But the moment you drill things and you go underground, you have water. Curtain wall is special, so they made one-to-one mock-up to see how it looks before they build. When you have a large construction, you try to test it before. And the last slide here, important. This is Posco high energy building. You could see this also in the ones we saw before of Richard Rogers or Chipperfield. All construction documents are on paper, and they are all line drawings. Those colors are applied by the construction guys to check for things, but on the site, we still use paper because the iPad is not practical. Well, again, being Harry Potter, it's not practical, it breaks, it's small, people don't see well, they get wet, they get dropped, and paper can be dropped. If it is get wet, you print again and use again. So still, 2020, paper line drawings are what we use in construction. And people happy. Again, I think everybody, almost everybody. So Yanme is back in graduate school, so you can see him at school. And other people, I think they're all working around. That's enough for today. 5 minutes over. I hope you enjoyed the lecture. I hope it was not too difficult. And as usual, if you have any kind of comment or question, you can write it in the email and I will address it. And if you want something special for tomorrow or next week, you can ask something you want to know or to elaborate on it, because the problem is open. Tomorrow I will elaborate more on the assignments. I will not have time to prepare much material because I have class all the time from now on. But whatever, hope you enjoyed. Please complete your assignments and concentrate 10 more days to finish the semester with success. Say goodbye in the chat. Take care and see you tomorrow, 10:30. Goodbye.